Hello, everyone. This is Aerodynamics 1 course. It is about incompressible flow. I am Dr. Samet Fanta, Assistant Professor from Aerospace Engineering Department, the first semester academic year of 2025 to 26, Bahar Dar, Ethiopia. So the course objectives is at the end of this course, the students will be able to understand the basic properties of fluid flow, understand the mass, momentum, and energy conservation laws, calculate or understand the velocity fields, the streamlines, vortices, and circulation, solve the aerofoil problems, understand the potential flow in 2D and 3D wings, know the lift and the drag of finite wings and infinite wings. The content of the first chapter of this course is it contains introductory part of the thought. The history of aerodynamics is also the part of this. The aerodynamic force and the moments. The aerodynamic coefficients, the non-dimensional coefficients of aerodynamic force and the moment. The pressure center, the aerodynamic center, the governing differential equations for continuity equation, momentum equation, energy equation. On that, the Euler equations, the Stokes equations will be discussed. The phase line, streamline, and straight lines of the flow, angular velocity, vorticity, and the strain, circulation, stream function, velocity potential, relation between the stream function and the velocity potential, the pressure and the velocity distribution on the bodies, various aerodynamic properties, and the pressure, density, velocity, and also the Mach number or the sound speed, which are part of this discussion. So let's directly start from the definition of aerodynamics. So aerodynamics is the study of motion of air and the force acting on the bodies moving through the air. So these bodies which moving through the air are maybe it can be an aircraft, it can be a missile, or it can be a rocket, it can be those racing cars and others. So it is just a study of the behavior of air as it interacts with solid objects such as an airplane wing, a car, or buildings. So aerodynamics is a branch of science and engineering that deals with the study of how gas particle, particularly air, interact with moving objects. The primary focus on understanding the forces like lift, drag, moment, aerodynamic force, and the motion resulting from the airs interacting with these objects like airplane, rocket, missile, is the primary objective of this course. So, because of that, this aerodynamics plays a crucial role in the design and performance analysis of aircraft and automotives. These fundamental concepts in aerodynamics is just airflow. When an aircraft moves through air, it experiences the effect of the fluid motion. This interaction between the aircraft and the air generates force that affects the aircraft's motion. So from this figure 1, what you can see is the interaction between the moving fluid, the aircraft which moves through the air, and the air, how it interacts with the aircraft wing. So this is just a CFD simulation, and the way how the air is interact with the aircraft. So aerodynamics are generally concerned with one or more of the following. One is the external flow aerodynamics, and another is the internal flow aerodynamics. So in the case of external flow over a body, the prediction of force, moments, and heat transfer on objects moving through fluid. the fluid which we consider here is the air. That is the state of external flow over the body. And another one is internal flow through the body. So that determination of the fluid flow characteristics within the rocket engines or within the enclosed passage, that is called the state of internal flow through the body. The dynamics of both liquid and gas are studied under the general topic called fluid dynamics. So fluid dynamics is subdivided into hydrodynamics, gas dynamics, and aerodynamics. So our main concern is on the aerodynamics, that is flow of air. Basic principles of aerodynamics are the fundamental principle of aerodynamics are derived from the laws of fluid mechanics and the thermodynamics. So this principle help explaining how the lift, drag, and other aerodynamic forces are generated and how our air behaves around moving objects such as aircraft, vehicles, or projectiles. So the basic principle are the principle of continuity or what we call conservation of mass, the Bernoulli's principle or the conservation of energy, and the Newton's second law or the conservation of momentum. So these three are the basic backbone of the study of aerodynamics. So we will drive the formula for each case. In the case of incompressible flow, as well as in the case of compressible flow. But in the first part of aerodynamics, the compressibility of the fluid is not considered, so that our fluid is incompressible fluid. So when we come to the continuity equation or principle, the continuity equation is based on the law of conservation of mass. It states that for a steady flow, the mass flow rate of air must remain constant from one cross-section of a stream tube to another. So for that, the mass flow rate, that dm over dt, which is equal to rho AB, is constant in this case. So on the momentum stream tube, we can observe the flow from one point to another, which is considered constant. So here, rho is density, A is the cross-sectional area, and B is the flow velocity. So this principle implies that when air flows through a constricted area, its velocity increases while pressure decreases. So this is called the conservation of mass, or it is the Bernoulli's principle. Yeah, that is actually mass or mass flow principle. The second principle is Bernoulli's principle, which is express the relation between the pressure, velocity, and the height or elevation in an inviscid incompressible flow. It is derived from the law of conservation of energy. That is, the pressure energy plus kinetic energy plus the potential energy is considered constant. So P plus half rho V square. Half rho V square is dynamic pressure, and rho GH is the potential pressure, so that which is considered constant. And this means that as the speed of the airflow increases, its static pressure decrease. The principle fundamental to the lift generation over an airfoil. So this is the explanation on the principle of Bernoulli's principle or energy principle. So P1 plus half rho V1 square plus rho GH1, which is equal to P2 plus half rho V square V2 square plus rho GH2. So point one is here, pressure one, velocity one, area one is here. Another area is here, it is at the narrow section. So flow velocity V1 here, flow velocity V2. And at the exit also there is another, we can consider this cross section also. So which is equals to constant. So this is what we call the Venturi tube apparatus to explain the Bernoulli's principle or energy principle. So in the Bernoulli's principle, it explains as a fluid speed increase, its pressure decrease. This concept is key to understand the lift in airplanes and how airflow works. So this is the lift generation. There is high velocity airflow at the top of the aerofoil and a low velocity airflow at the bottom of aerofoil. Consequently, the high pressure developed at the bottom and low pressure developed at the top. So that the differential pressure will help to lift the aerofoil to upward direction. So that is the Bernoulli's principle. The Newton's three laws are also an important component of for the study of aerodynamics. One is first law, that is a body remain at rest or in uniform motion unless acted upon by external force. So this represents two important equations. One is an object at rest. That means there is static condition here. And for the another case, uniform motion indicates that the velocity is constant, that the rate of change of velocity is zero. That means acceleration is zero. So static and dynamic equilibrium condition. And the second law is the force on a body is equal to the rate of change of its momentum, that F is equals to dmv over dt. That F is equal to mass times acceleration conditions, just the force F is equal to dmv over dt is the form of equation. So aerodynamic forces such as lift and drag arise due to the pressure and the shear stress distribution on the surface of the body. So which are helpful in the analysis. The third case is the law of inertia, action and reaction law. So for every action, there is an equal and opposite reaction. So it is the action and reaction are equal in magnitude and opposite in direction. So that the lift produced as the air is deflected downward by the wing, resulting in an upward reaction force. So the downwash and the lift creations are the opposite. So that is the third law principle, which is related with the lift. The condition in the combustion chamber also, when the mass of hot gas that are imparted through the combustion chamber or through the narrow section, then it imparts impulsive force that actually related with action and reaction condition. So this tells us that the third law of action and reaction condition for the rocket. So engine pushing forward and exhaust flow push backward. So the hot gas are pushed backward and the rocket moves forward. So that are action and reaction principle. Here also the deflection of moving air to downward, which creates downwash, and that action creates the reaction that moves the object upward. So that are also opposite force. Viscosity and boundary layer theory are also an important part of aerodynamics. So viscosity is the fundamental property of fluid that describes their internal resistance to flow or deformation. So due to the presence of viscosity, the shear force distribution happen on the aerofoil. So viscosity measure how easily one layer of fluid slides over another. When a fluid flows, adjacent layers move at different velocity, creating the velocity gradient. So as we observe from this, we have a velocity gradient that is this is just a velocity gradient, and we have delta. As delta approaches to y, what we can get is shear force tau is equals to the dynamic viscosity times dv over dy. So v is the velocity, y is the delta value. Okay, y is the so one of the fluid layer is considered stationary, and as the top considered movable. So on that, what we can get is the shear force. So the velocity gradient perpendicular to the flow direction is given by dv dy. Yeah. So the viscosity arises from molecular interaction with the fluid. For the gas, viscosity increases with temperature because of the molecular activities rising, while for the liquid, it decreases with temperature due to reduction in cohesion between molecules. Near the surface of the body, a thin layer of air called the boundary layer. So as we see here, these are the aerofoil. This is the aerofoil. On that, we have lower surface and we have upper surface. Okay, and there is a point where the flow velocity is zero, which is called stagnation point. So this is just explaining about the boundary layer. So the nature of layer or laminar or turbulence significantly affects drag and heat transfer characteristics. Okay, so we have laminar boundary at the initial. There is a transition somewhere, and then turbulence. And at high speed, we can observe such kind of turbulence wake, and which is contributing to the flow separation over the aerofoil. Okay, so now once we discuss these issues, let's come to the four fundamental forces of flight. In aircraft flight, we encounter four important forces. One is the lift, which suspends an aircraft in the vertical upward direction. Another is the drag force, which is the resistance or the opposite force for the forward motion. And the thrust, which is the force which enable an aircraft in the forward movement, or the one which is propelling an object forward. And the weight is the resistance due to the gravitational attraction, okay, which acts through the CG of an object. So these are the four forces. The aerodynamic forces are actually lift, drag are important aerodynamic forces. Thrust is the engine forces produced from the engine, and the weight is the summation of the component, which is acting downward. Okay, so these are the four forces. So lift is there, and these aerodynamic forces, lift and drag, are acts through the center of pressure, but the weight is acts through the center of gravity. So the weight is acts through CG, and lift and drag acts through the pressure center. And thrust is in the direction of the motion. So maybe velocity vector and thrust vector may not coincide. It may create some small angle. So that will be contribute to the performance equations of the force summation equation. So the two main aerodynamic forces are the drag force and the lift force. So lift is just, and drag are represented in the integrated form of effect of continuous distribution of pressure and viscous force that are acting on all exposed surface of the object. So lift and drag are always defined with respect to velocity of the vehicle. Okay, so this is the lift, the drag component is in this direction, so we may have total resultant aerodynamic force. This is total resultant aerodynamic force, which acts through the center of pressure, and drag is in the opposite to the flow direction. So these are the two aerodynamic force. So we can mathematically express lift by half rho v square SCL. So in this, rho is the density of air at different altitude, flight altitude. V is the flight velocity, and S is the area, or what we call planform area of the wing, and CL is the lift coefficient, the non-dimensional aerodynamic lift coefficient. So we will see what that non-dimensional aerodynamic coefficient. So lift is an upward force generated by the flow of air over the surface of an object. It is responsible for the enabling the flight and counteracting the force of gravity. So lift is the force that acts perpendicular to the direction of gravity and allowing an object to rise and remain airborne. Anything that flies must generate lift. In an aircraft, lift must be greater than weight to achieve and sustain the flight. Maybe at particular condition, lift is equals to weight and thrust is equals to drag condition may come at the maximum altitude where the aircraft is cruising. So maybe at constant velocity, at constant altitude, it may happen. But in most cases, this criteria must be satisfied to make the flying object airborne. Different aircrafts use various mechanisms to generate lift, and the airplane relies on the shape of their wings. So the lift generation of aircrafts relies on the shape of the wings, which are curved on the top and flat on the bottom. So this is what we call one is symmetric aerofoil and another is curved aerofoil. So the curved aerofoils are intentionally made for this purpose. These shapes cause the air to flow faster over the top and creating lower air pressure and higher pressure underneath. And the resulting pressure difference generates lift. That is what we have discussed. The second important aerodynamic force is drag force. So it is also half rho v square SCD. Now the difference is, in the previous case it was CL. Now here it is CD. So CD is non-dimensional drag coefficient, and the CL there is non-dimensional lift coefficient. So these things are interact to each other through the drag polar equation, so that we'll see them. So this CD is equals to CD naught plus KCL square is the drag polar equation. They will relate to each other. So drag is the resistance force experienced by an object as it moves through a fluid, and it acts opposite to the direction of motion and tend to slow the object down down. So knowing and minimizing drag is a crucial issue of the aeronautical or aerospace engineers or designers. Okay, our main intention is to minimize drag and maximize lift. Okay, so for that, a number of design philosophies are required. So these are various classification of drag. So drag is the parasitic drag, or in our drag polar equation, as I said, CD is equal to CD naught plus KCL. So CD naught is the parasite drag, and KCL square is the induced drag component. And further, the parasite drag also is classified into three: friction or foam drag, interference drag, wave drag. This wave drag is due to the generation of shock wave. Okay. again, the friction or form drag also classified into some three categories like skin friction, pressure drag, profile drag. Again, the interface drag also classified into the interface drag due to intersection geometry, because most of the aircraft component, like for example, wing is attached into fuselage, landing gear system or undercarriage system are situated into the fuselage, and tail sections are attached to the fuselage of aircraft, so that at the point where the two components are intersect, that we can have this intersection geometry drag or interference drag happen. Drag due to lift, that is CL square, is from this point. Again, wave drags are also categorized into drag due to volume and drag due to lift. So these are some classifications. So yeah, same classifications are here. So parasitic drag, CD naught, which include form drag, skin friction, and interface drag. Induced drag, which is known as lift-induced drag, CDI. So this is one part. So CDI is equal to KCL square. And K is another definition for K is 1 over pi aspect ratio, and Oswald efficiency factor is the K value. So that CL square over pi AR and E. So aspect ratio is by itself defined as the ratio of wingspan square over wing cross flank form area. So aspect ratio is equals to B square over S. Okay, so that is what. Wave drag is the third type of drag when an aircraft approaches to a speed of sound that is nearly after 0.82, the Mach number 0.82, such kind of drag will happen. It is just sometimes we call it as the drag divergence Mach numbers. So when it approaches to that, such wave will be formed, and due to that, it is called wave drag. So this is just drag polar, just to understand the drag polar. CD is equal to CD naught plus KCL square, and our K is equal to 1 over pi aspect ratio and also efficiency factor. So we have airspeed versus drag curve. On that curve, we have induced drag part of the curve, and the parasite drag of part of the curve is there. The intersection between two gives us the minimum drag point, velocity for minimum drag, and that is called thrust required minimum point. This point is called thrust required minimum point. And the total drag, the total drag is known as thrust required. The total drag is known as thrust required. So knowing the drag means we are knowing the, what you call that, thrust required also. So to determine the thrust, we have to determine the total drag. So thrust is another force from the force of light. So that thrust is the force that propel an object forward. And it is the opposite force to drag and is necessary to overcome drag and maintain forward motion. So in aviation, thrust is generated by jet engine, or it can be from the propeller or from various propulsive mechanisms. So propeller provides thrust for smaller aircraft, while jet engine power the large aircraft. So like the Boeing aircrafts, Airbus, they use jet engine. But small aircrafts like Bombardier, Cessna, and others may use propeller to propel the aircraft forward. So thrust equation mathematically given as m dot ve plus p minus pa the whole times ae. So the first part of thrust equation is called the momentum thrust, and the next is the pressure thrust. So the momentum thrust is the mass flow rate of uh, m dot is the rate of mass flow, and v is the exit velocity, p is exit pressure, and a is atmospheric pressure. A is exit area. So this is just in the case of this works for the rocket models. Okay. So thrust must exceed drag to keep the aircraft moving forward in the powered flight condition. So except for the cruising condition, in the powered flight condition, thrust must exceed drag. So in the absence of thrust, as in the glider, the aircraft will gradually lose speed due to drag and eventually descend. So this is gliding flight condition or unpowered flight condition. Weight is the force which is mass times gravity. So each part of the aircraft has weight and mass. And for some problem, it is important to know the distribution, especially for weight and the balance purpose. We must know each component of the weight: fuel weight, engine weight, wing, body weight, the pilot, passenger. Okay, so these all are the sum of the loads. The total aircraft maneuvering, we only need to be concerned with the total weight and the location of center of gravity. So CG must be known as the total weight where it acts. So this W is the total weight, and the point where it acts should be known, the CG location, for the stability and the control of the aircraft. So the center of gravity is the average location of the mass of any object. So weight is equal to weight of fuselage plus weight of wing plus weight of engine plus weight of pilot plus weight of fuel plus other components. Okay. In the case of fighter aircraft, we also consider the weight of munition which the aircraft carry. So this is for today, and yeah.